Hi guys, welcome back to another video of me teaching, and today I have this question on the board for you guys. So why don't we just get into the question? Well, I'm just going to say that this question is actually just me explaining to you what the Chinese Remainder Theorem is. And this is just an example of me using the Chinese Remainder Theorem to solve this question. So what I'm going to do is I'm going to solve the general form, and already with two congruence equations, you can already see how powerful the Chinese remainder theorem is. Okay, so if we just get into this question, then we see that since there are two congruence equations that x has to satisfy, then of course x will have to be the sum of two terms, right? So if we want the first term to be congruent to a mod m, then we need the second term to include m. Why? Well, because that means that if this includes m, then that will be irrelevant because it will be congruent to 0 or divisible. So it does not get in the way of the first term. Similarly, if we want the second term to be congruent to b mod n, then we want the first term to include n, so it doesn't get in the way of the second term. So then, because of this, we see that the first term will have a form of something p multiplied by n, and the second term will be something q multiplied by n. So now the real question is, what is p and q? Okay, well, how do we find p and q? Well, we want pn to be congruent to a mod m, right? Well, to have pn congruent to a mod m, then wouldn't it be nice if we have something congruent to 1 mod m? And then if we just multiply this something by a, then it's congruent to a mod m. And this is already a super simple example. So the question arises, what is this thing that is congruent to 1 mod n, which also includes n? I know it's very confusing, but this is actually pretty simple. Well, since over there it says that m and n are coprime, then we know that n multiplied by its inverse is congruent to 1. So it's n multiplied by its inverse, and this is congruent to 1. Now, this inverse is not those inverses you would find in calculus. It is actually just modular inverses. Okay, so now with this, if we just multiply both sides by a, then we see that a times n times its inverse is congruent to a mod m. Now, let's see if this satisfies everything. Includes n? Yes. Is congruent to a mod m? Yes. And is in the form of p times n. So we see that p is a times n inverse, so yes as well. Now, if you do the exact same procedure with q, then you find that q will be b times m inverse. So now we can actually write out the general form of x, and it will be a n n inverse plus b m m inverse. Okay, so now that we have this, the real question is, we have to find n inverse and m inverse. And to do that, I'll actually use these examples over here. So this is basically explaining you two things at once. So I'm going to rub this out, and then to find the inverses of a number, the way we do this is we first use ordinary Euclid's algorithm, and then we go backwards by using the extended Euclid's algorithm. So I'm not going to use that on n and m because that won't really work out. I'll just use it on 5 and 7 because we have to do that when we're solving the question as well, right? So we have to first use the ordinary Euclid's algorithm on 7 and 5. Okay, so how do we do that? Well, if you remember, the Euclid's algorithm goes like this. We write 7 as 1 times 5 plus 2. 1 is the quotient and 2 is the remainder. So we now have 2 focus numbers. And do you see a 1? No. And just a little note, when we see a 1, we have to stop and not 0 because m and n are coprime. So now, anyways, we have to keep continuing. So 5 will be 2 times 2 plus 1. Quotient remainder. Wow, we have a 1. So we stop there. And now we go backwards using the extended Euclid's algorithm. So we start from 1. What is 1? Well, 5 minus 2 times 2. Now, what is 2? 7 minus 1 times 5. So 5 minus 2 times 7 minus 1 times 5. Right? So this becomes, if we expand and collect like terms, 5 minus 2 times 7 plus 2 times 5. Collect like terms, it becomes 3 times 5 minus 2 times 7. And now this is what is called as Bezout's identity. So the reason why we're doing the ordinary Euclid's algorithm and the extended Euclid's algorithm is to get our Bezout's identity. And in our case, it's 3 times 5 minus 2 times 7. So now we can find the inverse of 5 and 7. So the inverse of 5 is 3, and the inverse of 7 is negative 2. And you can also write this negative 2 as 3 because we are in the realm of mod 5. So this can also be written as 3, but when I actually plug it into here, I will not use 3 because if we use negative 2, then we get the smallest possible value, or we can get the smallest possible solution to this equation using mod 5 times 7, which is 35. So now I will plug this into here, and then we can solve this question very easily. So we see that x will be a, which is 3, times n, which is 7, times 7 inverse is negative 2, add b, which is 4, times m, which is 5, times m inverse, which is 3. So if we multiply this out, we will get 21 times negative 2 is negative 42, and then plus 4 times 5 is 20, times 3 is 60, and this is 18. So 18 is the smallest possible solution in mod 35. Okay, so x equals to 18 is the final solution to this very interesting and powerful Chinese Remainder Theorem question. So thank you guys so much for watching, and if you enjoyed my video and you want more videos like this, please consider liking and subscribing. If you want to master something, teach it.